For most people, domain and range should not be looking like a new concept, though maybe the way we're approaching it in calculus is different than the way you've seen it before. But in general, when we're looking at domain and range, thinking about domain, thinking about all of the x values that we're allowed to plug in. And really that comes down to three things. And there are only three things that can go wrong with domain. It's the same three things in 16a as we're going to encounter in 16b, as we're going to encounter in 16c. There are only three things that can go wrong with domain when we're talking about functions. And those three things are kind of represented by, I'm going to just put up a couple of equations here. So if I said that f of x was equal to the square root of 16 minus x squared, then we're going to say the thing that could go wrong with domain is that we don't want to have negatives inside of the square root. I don't want negative numbers inside the square root. So for example, if I tried to put in 100 for x, 100 would not be in the domain. Because if I tried to plug in 100 for x, I'd have the square root of 16 minus, well, a huge number that for sure is going to leave us negative inside the square root. The two other things that can go wrong with domain, the most common one, or these are going to be the most common two that we're going to address in 16a. The other thing that can go wrong with domain is, let's say that I had something like 2x divided by 3 plus x. So here the concern with domain is that I can't have a number divided by 0. So that's the other thing that can go wrong with domain. I don't want negatives inside of a square root, and I don't want to end up with a number divided by 0. There's a third thing that can go wrong when we're talking about domain, and this is usually coming up in the context of logs, whether that's a natural log or a log with a base of 10. So if I said something like the natural log of 4 minus x, then in terms of a natural log, if I've got logs, I can't have 0 inside of a log, and I can't have negative numbers inside of a log. The truth is, this one we're usually going to hold off on because we're going to talk about exponential and logarithmic functions in 16b. So I wanted to point it out here because these are our three things that we should be looking out for in domain, but that last one we don't really use in the context of 16a very much. It can show up in this first chapter, but we won't, as we move through 16a, we won't be talking about logarithmic and exponential functions. So let's get some practice actually finding domain, and then we'll move on to talk about range. I want to take a look at this first function that I put up here. So I've got f of x equals the square root of 16 minus x squared. Well, if the thing that can go wrong in terms of domain is having a negative inside of the square root, then to look for the domain, so if I wanted to find the domain, then really what I'm saying is that I need 16 minus x squared to be a positive number. So it's got to be greater than or equal to 0. Now I'm including the or equal to because the square root of 0 is 0. If I take 0 times 0, I get 0 back. So the square root of 0 is 0, and we're thinking about domain with square roots. I'm going to want to include that 0. There are a couple of different ways to approach solving for this. We could move the x over, take the square root of both sides, but life gets messy with that because when I take the square root of something squared, I have to take into account both positive and negative values. So for me, I would rather look at this and say, hey, I've got a quadratic on one side and I've got a 0 on the other. I'm going to go ahead and factor this. So this happens to be the difference of perfect squares. So I can factor this as 4 minus x times 4 plus x. This next step, so I have two things that are multiplied together, and I need the result of that multiplication to end up being positive. Well, there are two ways that that could happen. Either when I plug in an x, this term is positive, and plugging in the same x, this is also positive. Positive times a positive is going to make it positive, or this is going to be negative and this is going to be negative. There are lots of different ways that you might go through that. It's possible that in a previous life, you had some cool skills to do this. I'm going to show you a technique that I use whenever I have inequalities, and we're going to keep using it throughout the 16 series at different points. And I just call it the number line technique. Now, sometimes people make a chart instead of a number line. Totally works too. I find the number line to be like the least amount of writing that I can do to get the point across. So I'm going to draw a number line. And the values that I'm going to put on my number line are whatever x values make one of these pieces equal to 0. So if I were to plug in 4 for x, 4 minus 4 would give me 0. So that's one of my zeros. And here I'd have to plug in negative 4 to get that factor to go to 0. We're going to develop some shortcuts for dealing with the number line a little bit later, but for now, what this has done is it has broken up our number line into 3 intervals. And in each of those intervals, I want to know if we plug in a value for x, is this statement true? Do these terms multiply together to be something greater than 0? So I'm going to choose some test points. And if I were to choose a test point of x equals 0, notice I'm keeping this way away from my number line because I don't want to confuse myself later about which values, I don't want to confuse myself later about which values are actually the intervals that we're worrying about. So if I plug in x equals 0, 4 minus 0 is a positive number, and 4 plus 0 is also a positive number. So I'm just going to put a plus on here. Now there's a question in the chat about a sign chart, and you can absolutely do more work and write more stuff and make yourself a big old sign chart with each of the factors and plugging in the values with each of the factors. The bottom line is the question here is to find the domain. The question isn't to make ourselves a sign chart. So you'll have to kind of balance how much do you need to do in order to get to that final answer. And for me, I'm going to write the least amount possible, but making sure that I'm going to get the right answer in the end. So if I pick another value out here, something bigger than 4, like 10, if I plug in 10 for x, 4 minus 10, I'm looking at a negative number. 4 plus 10, that's a positive number. A negative times a positive. I'm going to go ahead and stick a negative on here. And if I come over here and I pick a number less than 0, sorry, less than negative 4, so let's go with negative 10, and I plug that in. 4 minus negative 10, well, that's positive, but 4 plus negative 10 is going to be negative. So I'm looking at a negative out there. Looping this back around to the domain question, I needed this entire expression to be greater than or equal to 0. So I want the part in here where it's positive. Couple of options for how we write our answer. a lot of times in calculus, we're going to be expected to write our answer in interval notation. So we're going to say that the domain is all x values that are on the interval from -4 to +4. And when we write that -4 to +4, it almost looks like we're writing a point, but we're not. We're writing an interval of x values. Because this has that or equal to part, when I write this in interval notation, I'm going to give square brackets. So this is equivalent to writing it as x can take on all of the values between -4 and +4. Two different ways to write the same thing, but this top one is interval notation. Just in case anybody's asking you and specifying how you're going to write your final answer. Sorry, it's this stupid little Windows pop-up-y window that's making it so I can't see the chat. Okay. Questions about this guy before we move on?
I have a question about interval notation.
Yeah.
So if it was not or equal to, if it was just greater than, would it be parentheses?
Yep.
Okay, thank you.
Yeah. Okay, let's do another problem. I don't remember exactly what I had for that second function before, but it was something like this. And I'm going to call that good enough. So if I wanted to find the domain of this function, I'm kind of going to ask myself, okay, are there any square roots? No. So now I'm checking, is there a fraction? Yes, we have a division problem going on. So if I have a fraction, I don't actually care at all what the signs are. I can have a negative over a negative, a positive over a positive, right? The only thing that we're concerning ourselves with here is that that denominator cannot be 0. So if I went to write the domain, the simplest way to write this domain would be that x cannot be equal to -3. But let's say that I have actually been asked to write my answer in interval notation. So this is saying that I want all of the x values except -3. So if I were to think about that like as a number line, or sort of punching a hole in this number line at -3. When we write our answers in interval notation, we're always going to move from left to right. So on the left-hand side of this number line, if I went out here forever, I'd have -infinity. If I came out this way, I'd have +infinity. So when I go to write this in interval notation, I want this interval over here and also this interval over here, because the only thing that can go wrong in this problem is plugging in that -3 and ending up dividing by 0. So I'm looking at in interval notation going from -infinity to -3. And because we're not going to include the -3, we're going to put parentheses on that not brackets. And I'm going to take a little jump, which we use a union symbol to show that, and then go from -3 to +infinity. So these two are both correct answers, but the one at the bottom is the one you'd have to use if you've been asked to write the answer in interval notation. Let's do one more example. I'm going to make life get a little bit messier in terms of our domain here. And I'm going to make f of x equal to 2 minus x over 3 minus the square root of x. So if I walk up to this function and I'm looking at this and I'm thinking about domain, I'm thinking, do I have square roots? Yes. Do I have fractions? Yes. So I'm going to have to deal with both of those in the context of domain. Looking at this, I know that one restriction on that domain is that because I have this piece inside of a square root, no matter else what's going on, x is going to have to be greater than or equal to 0, because I won't be able to plug a negative number in for x. But at the same time, we also have that our denominator can't be equal to 0. So 3 minus the square root of x can't be equal to 0. And we're going to have to take care of both of these restrictions when we write the domain. Looking at the second one, my guess is that folks can maybe just see, type in the chat, what value of x would make this equal to 0? Totally, 9. So that means that if I were to think about this in terms of a number line, which you do not have to, but I know that I need x to be greater than or equal to 0. So here's 0, and I have like a filled in dot because I have the or equal to. But I have to come over here and punch a hole at x equals 9. So I know that I want all this part where it's greater than 0. I just have to skip over the 9. And when I go to write this in interval notation, that's going to look like we'll include the 0, head out to 9, take a little jump, and then go 9 to positive infinity. In the scheme of things, although sometimes writing our answers for domain problems can get a little bit messy, with domain, we have this really clear set of rules. And I'm about to throw those all out the window because when we get to range, we don't have this nice set of rules. I'm going to pause here just for a second in case there were questions about this. Not seeing anything in the chat. Let's move on and talk about range. I'm actually going to go back to example 1 now, or at least that first function we had, and think about it in the context of range. So if f of x is the square root of 16 minus x squared, so we have this clear list. If I'm doing domain, I'm thinking about, I can't take the square root of a negative, I can't divide by 0, I can't take the log of 0 or a negative. When it comes to range, we kind of have 3 things also. The first option is we graph it. And if we can graph it, then the range is answering the question of which y values does the graph of that function actually reach. Option 2 for range. If it's possible to find an inverse, then we can find an inverse for the function. Now, when we find an inverse, that first step that we talked about last week, or you talked about in calculus, or you remember from pre-calc, usually when we start an inverse question, we take the x and y and we swap them. Well, that means that in the context of domain and range, since domain goes with x and range goes with y, when we swap them, that means that instead of finding the range of the original function, we can find the domain of the inverse. But not every function has an inverse, and not every function is something we know how to graph. So the third option for finding the range is we stare at it and just see if we can figure it out. I know that doesn't really feel like a technique. It's totally a technique, and it's a technique we're going to use a lot in 16C. But for right now, we're mostly going to rely on, can we graph it or can we find the inverse? So thinking about this, I'm going to go for graphing it because I happen to know what this looks like. And to help you see what it looks like if you don't immediately see what the shape is, I'm going to change my f of x to a y so that I can square both sides. And then add the x squared over. And recognize, hey, that is a circle with a radius of 4. This, because I've got a square root, means it's not the entire circle. This is telling me it's only the top half of a circle. So if I were to sketch this, this is a circle centered at 0, radius of 4, but we're looking at the top half of it. And if I were to write the range in interval notation, I would say that the lowest y values anywhere on that portion of the curve are down here at 0, and we go all the way up to 4. You could also write the range as saying y is between 0 and 4. Again, that sort of comes down to whether you're being asked to give an answer in interval notation or not. Okay, I saw a question come up on the chat, but I wanted to get through this one first. So question is about inverses. Graph has to be 1-to-1 to have an inverse, totally. Can you find an inverse if something isn't 1-to-1 just by adding additional restrictions? Sure. Yeah, okay. And then the question, or at least a follow-up on there, was sort of how would you decide if the function was 1-to-1? Well, I made the claim that this function did not have an inverse. This might be a really terrible function to show that it's not 1-to-1, but I'm willing to give it a shot. So since we already know what the graph looks like, I can graphically see that the function is not 1-to-1. Our graphical version of testing for 1-to-1 is to say, does it pass the horizontal line test? If I draw a horizontal line on the graph, is there anywhere where that horizontal line would touch the graph twice? And there is. In fact, pretty much everywhere on this graph, if I draw a horizontal line, it's going to touch the graph twice. So I know that this function is not 1-to-1. But how would we show that with algebra? So in general, if I'm trying to show that something is 1-to-1 or is not 1-to-1, I'm going to start in the same place. And I'm looking to start at, if you like subscripts, we can use subscripts. Otherwise, you can just use A and B. The mathier thing to do would be to use subscripts. So if I start with f of x1 is equal to f of x2, and I kind of simplify both sides of this equation, and we get down after doing a whole bunch of algebra, and we get down to x1 is equal to x2, then we would conclude it is 1-to-1. If we can't get to here, then it is not 1-to-1. So let's see what happens if we mess around with it for this function. So f of x1 would look like the square root of 16 minus x1 squared. And if I were to set that to the square root of 16 minus x2 squared, then I can certainly square both sides of this equation. and end up with 16 minus x1 squared is equal to 16 minus x2 squared. And then I could subtract 16 from both sides and end up with negative x1 squared is equal to negative x2 squared. And then I could multiply both sides by -1 so that I have x1 squared is equal to x2 squared. And this is the point at which I can show that it's not one-to-one, because I claim there are two solutions to this. X1 could be equal to x2, or x1 could be equal to negative x2. And both of these are solutions to that equation. And since we ended up with two answers, not just one, I know that f of x is not one-to-one. Which loops me back around to, since it wasn't one-to-one, we weren't going to be able to find an inverse anyway. So it's a good thing we knew what the graph looked like. Now to the second part of the question in the chat around, can't you make a restriction on the domain? Absolutely. So we could make a restriction on the domain, for example, to say in this case, we would only consider positive values of x. Well, if we only consider positive values of x, then this last piece is no longer in play, which means it would be one-to-one if we only consider that restricted domain. I will also say that's probably mathier than we most of the time need to worry about in 16a. Okay, I want to go do another range problem. I want to take a look at my example 2 one. Okay. So now if we go back to my example 2, or at least that second function we were working with, f of x equals 2x over 3 plus x. So I'm going to look at this and say, well, if I'm going to find the range, the first option is to graph it. And we will get to a point where you're going to be able to look at that and say, yes, I know what that graph looks like. Right now, you might think to yourself, yes, I can plug that into Desmos and see what that graph looks like. And that's totally an option in terms of finding the range. But I want to instead take a look at this and find the range by first finding the inverse. So if we wanted to check if the inverse exists, we could quickly check to see if this is one-to-one. Should we do that?
Oh my God, Nico.
Sorry. Someone said something, but maybe they accidentally unmuted themselves. Can I get either a reaction of a thumbs up or an actual thumbs up? Do we want to see, should we show that this is one-to-one? I see some thumbs up. Let's go for it. Let's show this thing is one-to-one so we can find an inverse. So I'm going to start off the same way every time. I want to start with f of x1 is equal to f of x2, and then we just see what happens. I need a little more space to stand. Sorry. There we go. Okay. I'm looking at 2x1 over 3 plus x1 is equal to 2x2 over 3 plus x2. That looks terrible. But if I'm going to solve this thing, personally, when I see fractions, I am thinking about, if I see fractions and I have an equal sign, I'm thinking about what can I multiply the entire expression by to get rid of those fractions. Meaning I'm going to multiply by 3 plus x1 and also by 3 plus x2. And if I do that on both sides, then I won't have fractions anymore. On the left-hand side, that 3 plus x1 is going to cancel out, and I'm going to be left with 3 plus x2, and then I'll still have that 2x1 on top. Over here, the 3 plus x2 part will cancel out, and I'll have that 2 times x2, and then we'll have the 3 plus x1. Next up, I'm going to distribute everything out because my hope is whenever I'm trying to show this one-to-one thing, I'm hoping to get down to x1 is equal to x2. This is the goal. It's good to have goals in life. Okay, so if I distribute this out, 6x1 plus 2x1 times x2, and over here I'll have 6x2 plus 2x2 times x1. Well, the good news is, since when we're multiplying things, we can rearrange them. This term and this term are the same. I've got it on both sides, so when we subtract them from both sides, it's going to go away. If I subtract a negative 2x1 x2, then I'll have 6x1 is equal to 6x2, which means I can divide both sides by 6. And what do you know? I'm down to x1 is equal to 2. This was, in fact, 1-to-1, which means we can find an inverse. Now let's proceed to find an inverse. If f of x is equal to 2x over 3 plus x, then personally my first step for finding that inverse is going to be to swap the x's and y's. So to find the inverse, when I swap the x's and y's, I'm going to be left with x is equal to 2y over 3 plus y. I'm a little short on space. I wish I was teaching in a classroom with a giant whiteboard at the front of it or something, but I'm not. I'm in my bedroom. So I'm going to erase this part because I need the space. Okay, next step, if we're finding the inverse here, step 2, I want to rearrange to get y by itself. And right now I'm looking at x is equal to 2y over 3 plus y. And I'm going to look at that and say, hey, I've got a fraction and an equal sign. I want to multiply both sides by something to get rid of the fractions. So I'm going to multiply both sides here by 3 plus y. On the right-hand side, that 3 plus y over 3 plus y, it's just going to leave me with a 1. So I've got 1 times 2y. And over here, I can go ahead and distribute that out to end up with 3x plus xy. I know it seems dumb, but I like to actually write out step 2 because sometimes I get to this point and then I'm like, wait, what was I solving for? We're trying to get the y by itself, which means in terms of this equation, I want all the y's on one side and everything without a y on the other side. Personally, I look at that and say, I'm going to put the y's on the right-hand side. But I've found over the years that that makes students uncomfortable because people would like the variable we're solving for to end up on the left-hand side of the equation. the mathematician-y thing to do is definitely to move the y's to the right and to avoid having additional minus signs. But anyone have a vote? Left side, right side? Where should we put this? Really, this is just my check to see if people are still awake. Move it to the right. Yes, less negatives. Thank you. Think like a mathematician. Let's move those y's to the right. So I am going to end up with 3x is equal to 2y minus xy. At this point, because I'm trying to get the y by itself, I'm going to go ahead and factor the y out from both of those terms so that I've got y times 2 minus x. And my last piece here, to get that y by itself, I'm going to divide both sides by 2 minus x and end up with y is equal to 3x divided by 2 minus x. That third step that sometimes we don't even write as a step when we're doing the inverse is to rewrite the y, because it's not actually y from our original function. It is f inverse. Now that I have an f inverse, I'm going to stare at that and say, we swapped the x's and y's. I was trying to find the range, which went with the y, but we swapped it into the x. So now I need the domain of f inverse. Because I've got a fraction, the only thing that's going to mess the domain up is if we tried to plug in 2 for x. So I know that in terms of f inverse, the domain of f inverse would be that x cannot be equal to 2. So the range of my original function is going to be that y cannot be equal to 2.